Okay. All right. Okay, welcome. We're going to do the exam review. Thanks to Mario, he's going to help videotape this. There's people that can't make it today, and we're going to do it as a service to them, and then also kind of a test for maybe the future as far as using this all the time, so that we can have something that you can look at, or if you're missing the exam reviews, you can come check it out online. So what most of you know about our website already, and you've been probably watching Physics 121 lectures online. Those are offered there. I'll be on the same website. We'll just be on the latest listing, and maybe I'll start a playlist. So to see where people are at, we've got an exam coming up on Monday. We've got some hard stuff. This has got the reputation as the toughest stuff. Everything is kind of built the whole semester. Usually when you look back at the first stuff, it seems hard at the time. Later on, as you get ready studying for the final, you're going to look back on that and it's going to seem relatively easy. And one reason is because you've been using that stuff all along. And everything we've been using up till now, we're going to keep using. And so that's because of all this building of things you need to know, it seems like it's very complicated. And right now we're in a position of where we're trying to pull this all together, getting ready for next Monday's test as well as the final. So we're kind of touching on all those things. Again, anybody coming in, you can pick up copies of the practice problems. We'll be talking about these. We won't do them all. Primarily the reviews, we want to try to get kind of the big picture, dealing with the setups of problems. You've got my solutions if you want to look and pick through the details. Okay, we're going to start with momentum. And we just define momentum. This symbol P we'll be using for momentum, I'm not sure where that came from, is going to be in this triple bar. Means it's kind of the definition. It's the mass times the velocity. So one simple thing you can do is take the derivative of the momentum with respect to time. And if you take the derivative of the mv, the mass usually doesn't change, and so that's a constant. And then it's just m dv dt, which is nothing more than ma, which we know from Newton's is the net force. So this, the idea that the net force is equal to the time rate of change of the momentum. I'm leaving off, these are all vectors, so I should have that on there as well. This is going to be true, and this is actually more of a modern definition of force. You've been hearing the mantra throughout the semester, F equals ma. It turns out that when we get into next semester, when we get into relativity, we're going to see the mass isn't constant. But Einstein will use the F equal to the time rate of change of the momentum as the definition of force. And so it's going to, in a sense, get redefined this way. For right now, for us, as long as the mass doesn't change, it's going to be the same thing. Okay, so that's a bit of a look ahead. But let's look at kind of what you're expected to know for Monday. If we have something, let's say a tennis ball and a tennis racket, and you smack the tennis ball, it could be coming in at this thing, and I hit it, and I return this thing. This tennis ball could, it could have a change in momentum. Couldn't it? Right? I mean, it's got a momentum coming in, mv, and I smack it, and I send it off. I could change its momentum. This idea that we're going to have some kind of a collision, and we refer to these as collisions, between this is, we could look at that as a force with respect to time. It's something we're going to call an impulse. And the idea that that force, or force curve, maybe I'll do the force in red, that all of a sudden this ball could encounter the racket, in which we could have a rather complicated interaction between the tennis racket and the tennis ball. We can define the impulse, and we're just going to, again, use this triple arrow indicating that, triple equality, indicating this is a definition, is going to be defined as the integral of the force applied to this thing with respect to time over this amount of time. So the idea of the integral, again, these are also going to be vectors, this impulse is the area under this curve. Okay, so that's rather strange when you think about it. I may not know all the particulars of this collision, but I can still talk about doing this integral and the idea of doing it. Now, the idea behind it is, again, the idea that force should be the integral of dp dt, and if I'm integrating with respect to time, I'm just going to get the integral of dp, which is equal to my change in my momentum. And I should watch carefully. I should go from time t equal to 0 up to some time t, which would be this time of the impulse, or maybe a delta t here. And that's going to cancel here. We're going to end up with this change in momentum, which would go from p initial to p final. So delta p is p final minus p initial. Again, I want to emphasize these are vectors. We can get a little sloppy here. In the past unit, we went into energy, and energy was convenient in that it was a scalar. But with momentum, we're back to vectors again. So we've got this rather convenient triad here. This impulse is equal to this idea of the integral of f dot dt, this actual, and that's equal in turn to your change in momentum. And so you want to kind of keep this as this impulse momentum idea together. Sometimes in this collision, we don't know all the particulars of the collision, but we can sometimes talk about maybe something like the average force. Imagine if I held some force along here over the same amount of time. That would be what I would call my average force. That would mean that I'd have to be able to take this area and fill that in so that the area or the impulse would be the same, whether it's a spike in the force or whether it's just a constant force applied over that same amount of time. So sometimes we will just say this is going to be F average just times a time, or a delta t, and that will be equal to your change in momentum. Sometimes you'll figure out what the change in momentum is, and then the question would be, well, what is the average force? Because we can't necessarily get back to what's going on. Okay, now, this idea of an impulse changes the momentum. But you hear a lot of talk, and you've done a lot of homework with something called conservation of momentum. So what's going on here? Is momentum conserved here? No. I mean, the tennis ball is coming in. It's got one momentum. It goes out. If it was conserved, that means the momentum doesn't change, right? It definitely changes. So, wow, what do we do for this idea of conservation of momentum? Here's an idea. Suppose we have a system, and this is when we use conservation of momentum. If I have, let's say, a ball coming in here and another ball coming in here with different velocities, I could call this one M1, and this is V1 initial, and M2, V2 initial. They're going to come along, and maybe that they're going to make contact with one another, and maybe these two balls are going to collide. Imagine I've got these two racket balls, and they're flying in. They're going to collide. As they're colliding, the balls are kind of flattening out. There's forces between them, and then they're going to spring off and go off in different directions. So they're going to take off with this collision, going off. This one going that way. This one probably going off like this. And we're going to have, this is going to be V2 final. This is going to be V1 final. And this collision, if we focus on that, we have what's going on are going to be impulses between these two things. We have Newton's third law. With this is the force on one is going to be equal and opposite the force on the other one. So the force of ball 1 onto ball 2, let me call that F1. Or actually the force on ball 2, I better call that F2. And this reaction force is going to be the force on ball 1. And by Newton's second law, or third law, excuse me, that these forces should be equal and opposite. Okay? And these forces that are equal and opposite, they're going to be throughout the whole impulse. There could be an impulse on one that could be rather complicated like this. It would be the opposite direction for the other one, but of the same magnitude. So we'd have to say that I'll just use I for impulse of one. Maybe I better write impulse, so I don't confuse that with moment of inertia. Impulse on ball 1 will be equal and opposite the impulse on ball 2. Again, these are going to be vectors, simply because the forces are equal and opposite. The impulse on ball 1, we go back to this impulse momentum, that should be equal to your change in momentum of ball 1, is equal and opposite the change in the momentum of ball 2. Well, change in momentum was P1 final minus P1 initial is equal to minus, this is going to be P2 final minus P2 initial. And playing with the signs, let me take this, I've got P1 final here, and I'm going to bring this minus P2 final over to the other side. That's going to become a plus P2 final. Again, all of these are vectors. I'm going to take this one as negative, I'll take it over to the other side as positive, P1 initial. And a minus makes this a plus P2 initial. So when we look at this as a system between the two of them, their momentums together, this is the P initial of the system of the two is equal to, excuse me, this is the final of the system is equal to P initial of the system. And so we say momentum is conserved. That means it stays the same. The reason it stayed the same is not that individually their momentums didn't change. They did. But collectively, the total change for both of them together is 0. One is plus, one is minus, and when they add up, and this is usually the form we'll do our problems in. We'll just say, well, the initial momentum by adding up the momentums of the pieces is equal to the final momentums, and set those two things equal. And this is what we call conservation of momentum. Okay? Okay, so a relatively simple idea. Now the check for this, when momentum is conserved, this is going to be the acid test. When we had a collision like this, we have a collision, these are what we call internal forces to the system. They're acting between one another. When we do momentum conservation, we focus on the whole picture, and we look and see if any other forces are coming in from the outside. As long as there are no other forces coming in from the outside, all forces we say are internal to the system, then momentum will be conserved because of this idea of action-reaction. Everything can change, but add up all the changes and it ends up being no change for the system. Okay, so let's put this idea to use here. You've got some problems here, and I want to I've got a lot of ground to cover, but I want to allude to some of them so that you can be looking at them. I've got, I've got kind of two sets of problems. Anybody not pick them up? I've got them up front here if you want to get this. I'm talking about this first one I call test number 3, practice problems. I've also got one that says extra problems. Let's do this one with practice problems. Let's take a look at problem number 1. That seems appropriate. So this is number 1. We've got just a block sitting on the table. We've got a bullet that's streaming along with high velocity, 400 meters per second, a 12-gram bullet. Let me just, I want to kind of keep the focus on the big picture. You got my notes on the details. So I'm just going to call this one small m, and let me call this v naught, the speed that it's coming in at. And this block is just sitting here. It's called big M. This bullet is going to come screaming through here, and I'm going to kind of take an imaginary picture. You want to think of momentum. We want to think of the before, and then we want to think of the after of this. Think of like two snapshots of what's going on. This block is here. The bullet rips through here. It's headed off. It has a reduced velocity. It's now down to 100 meters per second. So I'll call that, let me just call that V1 final. This other velocity here is going to be, I'll call this V2. Those two together are going to comprise the final momentum. Now, as this bullet is going to rip through this block, there can be forces. Frictional forces as it rips through. It does slow down. This is something we call an inelastic collision. It doesn't bounce off it. It literally rips right through it. But there are frictional losses, and there's heating taking place as that bullet goes through. But let's focus just on the momentum for right now. We could say the initial momentum, and this would be of the system, would be mv naught plus, I'll say, big M, and its velocity is 0. And so that's my initial momentum. This is strictly, we're playing with this problem strictly in the x direction. If you want to go ahead and put in the subscript x, that's probably not a bad idea to do that. And P final, and that's going to be in the x, is going to be equal to now this mass times V2 plus the small mass of the bullet times V1 final. And the idea of conservation of momentum between the before and the after, that's where we focus. We set these two things equal. The initial in the x is equal to the final in the x, and we have this mv naught plus m, well, that's going to be, this is going to be obviously 0, and that's going to be equal to mv2 plus mv1 final. The thing that he gives you in the problem, he tells you what the initial speed of the bullet is and the mass of the bullet, the mass of the block. The only thing he doesn't tell you is the velocity of the block. Okay? And then so you end up finding what that velocity is from momentum. Now this problem actually goes on, and you'll notice that this block is going to fly off the table. So that's actually another part of this, that the block will now be leaving the table with that velocity. And it's going to fly off and now is going to hit the floor over here somewhere. And it actually wants to know where it's going to hit the floor. Now, that should be way old stuff here. But you better know how to do it, right? Okay, if not, on Monday, you will need to know it for the final. So how do you do something like that? Okay, now the time that it's in the air, the whole time that it's in the air, is it going to keep going at this speed? Okay, it's going to go at that speed the whole time that it's in the air. You want to say how long is it going to be in the air? That would be the same as if I just took something and I dropped it, that amount of time it's in the air, and then you can just use that this distance is equal to the velocity that it's traveling, v2, times the time that it's in the air. And again, we'd find the time as it would be to fall. Okay, there's all kinds of problems like this that could come up. We want to focus on the new stuff, but keep in mind that everything has been building the whole semester, and all of this stuff is still fair game. Okay, so a little reminder, you may want to look at your linear kinematics as well. Okay, let's look at a little tougher problem. There's another problem that's very similar to that. In fact, it's the next one, number 2. And I want to kind of allude to that one as well. Okay, this is a car and a truck traveling, where you've got this truck coming in, and it's going to collide with a car. They're both traveling, I think, the same speed, 20 meters per second. 20 meters per second. They're going to come in and they're going to collide. So we've got a momentum here. This is the momentum of the truck is traveling in this direction. Maybe I should put some colors on this so we can be clear on that. There's going to be a momentum, mass times velocity. The mass of the truck was 1,500 kilograms. The car is just 1,000 kilograms. They're both traveling the same speed. Their momentums, they will collide here at some point. And then the idea is what's called a totally inelastic collision, because they're going to stick together. They're going to stick together, and actually this is one of the most easy ones to get. The idea that they will go off at some angle. Let's see, they're slashing like this. It sort of makes sense they're going to go off as a crumpled mess off in this direction with some final speed, which we need to find. And they're also going to go off at some angle, theta, which we also need to find. And momentum applies to this in that the collision is between them. It's this idea of this internal force between the two, so we can justify that the momentum is conserved. And in this case, it's a kind of a 2D problem. We can probably think in terms of like the x-axis and the y-axis and break these things down. If the momentum, the initial momentum, is equal to the final momentum, these are as vectors, it's best to think in terms of maybe the momentum in the x, do the x components. And so I would start off here with, I'd have 1,000 kilograms times the car times 20 meters per second. That's its momentum. It's in the x direction, so if you want to use an I-hatch, you can do that. Right now, I think it might be easiest just to think in terms of the momentum in the x and the momentum in the y. We can also get the initial momentum in the y. Let's look at that. That is, oh, excuse me, I've got another one in the x. You're supposed to stop me, right? Okay, I got the car in the x. What about the truck? Does it have one in the x? Okay, and this was coming in at, angle was 45. I don't know, looks like these are almost the same angles. He's coming in at, this is a 45. In the x direction, that has an x component, so that's going to be plus 1,500 kilograms, again, times 20 meters per second, times the sine or cosine, depending which angle you're talking about here. In this case, this angle, it'll be the cosine of 45 degrees, and that would be the initial in the x. That should be equal to the final in the x, but let's come to that. Let's take a look in the y direction. That the car didn't have, that's 1,000 kilograms times, and it would not traveling at all in the y direction, zero velocity. The truck has got a velocity of, it's 1,500 kilograms times 20 meters per second. The y component is going to be the sine of 45. Oh, is that, should this be a plus or a minus? Minus, yeah, it's headed in the negative direction, so this should be a minus. Okay, and then that's going to be the momentum in the y. Both of these should be equal to the final momentum. This one in the x, and in the x direction, we could say that that's going to be v final times the cosine of theta. And in this one in the x, cosine of theta. In the y direction, this is in the negative direction, so it's going to be a minus v final times, let's say, the sine of theta. Okay, any Oh, yes, thank you. Yeah, thank you for catching me. I get thinking about what I'm trying to say and I forget all that. Yeah, it's going to be v final times the mass. What mass is it? It's the two of them together. They're a crumpled mess. That's 2,500 kilograms. Okay, and that's times the cosine of theta. And this one's v final, again, times 2,500 kilograms. Yeah, times the sine of theta. Yeah, definitely. Don't let me get away with this. Okay, as far as the numbers, Usually I don't want to do too much with numbers, but let me pull some numbers here and just do part of this. I see that P and the X, let's see. Okay, I get all this together. All of this, when I stick in the numbers in the calculator, I came up with 41,213, and that's going to be in kilograms, meters per second if you're using units. And this will, of course, still be V final times 2,500 times cosine theta. So I've got kind of this one that I want to look at. And I want this one here is going to be, this is 2,100 in the Y. And I'm pausing. Okay, so this should be a minus 2,100. 213 is equal to a minus V final all over 2,500 sine theta. And I can get rid of those minus signs if I want and just talk about that. Okay, I'm kind of bumbling through this. I hadn't practiced this problem in a while. Essentially, we've got two unknowns. We've got two axes, x and y. This will allow up to two unknowns. Our unknowns are theta and V final. We can get at them, and we've got these two equations, and you notice one reason I stuck in these numbers is because I want to emphasize what we don't know. We don't know this final velocity, and we don't know the angle. Same thing here. We don't know the final velocity. We don't know the angle. So we need to solve for them, and there's lots of ways you can do it. I'll show you a slick one that I kind of like is solving for the angle. If I take this one, that's 21,213 is equal to V final times 2,500 times the sine of theta. And I look at this one and I see that that's 4,100. 213 is equal to V final times 2,500 times the cosine of theta. And I say, wow, these are both equal. And what if I take this one and I divide both sides by 4,100? This one is equal to this one. Students don't always like this, but do you see why that would be true? This is equal to that. I'm going to divide them both by 4,100, 41,000. And this is equal to that, so I'll replace that. Here's my motivation. These unknowns, which I don't know, drop out. Also something I knew, but I don't have to calculate. I've got this. I can get that the tangent of that angle is the ratio of these two numbers. So I can easily do the arctan and get what theta is. And then I won't take through the details on that. Once I have that angle, then I can go back into either one of these two equations. Sticking in the angle, I can then go ahead and solve for V final. So, the negative, I had a negative here on both sides. Negative and a negative, and I ended up just wiping those off. Okay, so you can see my notes about more details on that problem. But anyway, I didn't mean to do as much with that. Now, we have different types of collisions that can take place. This idea of a collision, it can be what we call elastic, or when we say elastic, we mean completely, totally elastic. And here would be an example. Let's say we have a rubber ball and I drop that. Is this elastic?
Yes.
Okay, I like the term semi-elastic, although the book uses two. One either elastic, which is perfect conservation of kinetic energy. A perfectly elastic ball would be one that I could take it and I could drop it and it would come right up to the same place. I wouldn't lose any energy in the collision. In reality, this ball maybe gets about 60% of that energy, so it loses about 40% in the bounce. So energy, we say, is not conserved, or at least kinetic energy is not conserved. Total energy, as long as we include heat, would be conserved. Now, this whole idea with a collision and this idea of internal forces, these forces can be due to anything, whether they're elastic or they're inelastic. It doesn't matter. The only thing that would be different if it's an elastic collision is that we have an additional thing that kinetic energy is conserved. So if we had the kinetic energy of this plus the kinetic energy of this coming in, that should equal the final kinetic energy of those two things going back out again. Usually we're somewhere in between. This crumpled mess with the car is something we call a totally inelastic collision. A lot of energy goes into heat. Not all of it. We still end up with some kinetic energy at the end, but we can predict the amount of heat that's generated. In fact, you've got another problem here. I've got it on the extra problems, is one with bullets hitting a tin can. Let's look at that for a second. Okay, now this one is number 1 on the extras. And again, we've got this bullet. It's coming in. He's got a 25-gram bullet, 0.025 kilograms. It's traveling at 300 meters per second. It's going to come in and strike the can. The can is sitting here. So again, you want to think in terms of this is kind of the before. And then you want your after picture where this bullet came in, struck the can. The bullet is going to ricochet off and go off in this direction. The can goes off in this direction and with some velocity. And we've got the velocity of both, really. We've got this initial here. Maybe I'll call this one, let's say, V1 of the bullet and V2 of the can. He does tell us that this angle is 20 degrees here and that this angle is like 40 degrees. And we need to find these two velocities, not because he asks for them directly. What does he ask for? Yeah, he actually asks for how much heat is created in the collision. So the first thing we're going to do is take a look at this from conservation of momentum between the before and the after. Here we have momentum in the x direction. P initial in the x is just equal to 0.025 times 300 meters per second. And then that's equal to the final in the x, where we're going to have these two. Again, this is, let's see, 0.025, and I believe the can is 0.2 kilograms. 200 grams or 0.2 kilograms flying off that way. And so we're going to end up, let me write it out. I have trouble talking at the same time I'm writing or I make mistakes. I'm going to have a mass of 0.025, I'm still talking, times V1 times, I'm going to go with the cosine of 20 degrees plus this one, which is going to be 0.2 times V2, let me leave off the units for convenience, and cosine of 40 degrees. Okay, so we've got that one. I don't know what these, again, these are my two unknowns. P initial in the y is what? Yeah, there is nothing traveling in the y. This is a big fat 0. This should be equal to the final momentum in the y. If we look at this one has a component in the y, so that's going to be 0.025 times V1 times the sine of 20 degrees, and that's in the positive direction. This one is headed downward, so that's going to be a minus, and that's 0.2 times V2 times the sine of 40 degrees. Again, we have these as unknowns. Right now it's a math problem, and I'm not going to try to tell you how to do it. Whether you want to solve by substitution, solve one of them, let's say for V1 and stick it in, and solve then for V2. I'm going to leave it at that and just say, well, we'll get V1 is equal to something and V2 is equal to something. And let me just pick up my numbers here that I came up with. The extra problems. Okay, I've got the velocity of the can was 14 0.8 meters per second, and I came up with 20. The bullet is still traveling pretty fast, 2.7 meters per second, according to the way I worked it out. Then what do we do to determine whether we've lost energy or how much heat is generated? Okay. Okay, yeah, we want to look at the initial energy and the final energy. One way we can do that, we want to focus primarily on the kinetic energy. The kinetic energy initial should be equal to your final kinetic energy plus any heat that you've generated. Does that make sense? It was just the mechanical energy. So we'd have the initial kinetic energy of the bullet itself. Okay, so that's going to be this 1/2 the mass of the bullet, 0.025 times v squared. 300 squared is equal to the final kinetic energy. You get the two of these. Now we're going to have two terms. I'm going to have a 1/2 of 0.2 for the can times its velocity, 14.8 meters per second. I'm going to square that. Plus, I have to get the kinetic energy of the bullet. We have both of them together. 1/2, and that's 0.025 times its speed of 2.7, and that's squared plus heat. And so now it's a matter of just solving for the heat. And I'll do that, and whatever my answer was I came up with heat of 483.2 joules. Okay. As you check your numbers, these extra problems I did just this last week, and I didn't have a chance to go over it, so if I messed up on some numbers, don't be too surprised. Don't like lose any sleep over it. Call my attention to it, though, if you've found any errors that I made. Okay, so that's kind of a quick look at momentum, conservation of momentum with the typical collision. And you're very likely to get a problem like this. And so here's kind of 3 examples of how you might see it.
John,
yeah.
Can you go through that problem again real quick without all the calculations?
Okay, yeah, I think that's good. We tend to lose the details when we stick in a lot of numbers. Most of them I'm not going to be doing a lot with numbers. We look at the initial momentum. Here we have strictly momentum in the x direction. We have no momentum in the y direction. So this thing's at rest, so we have the mass times the velocity. When we end up with the final situation, again, we're going to look at this picture. We're going to look at the x terms and set them equal to the initial x terms, and the y terms equal to the initial y, which was 0. And each of these things, we've got really 2 unknowns we can typically solve for. He gave us the angles. In this case, he's asking for those velocities, or indirectly. We need them for the next part. And we're setting up both momentum in the x and the momentum in the y. So that really gives us 2 equations. And with those 2 equations, we can solve for 2 unknowns. Sometimes, like the car, he asks for the angle and the velocity. Sometimes here he's just asking for the velocity. So he's limited on what he can give you. The nastiest type of problem where it's totally elastic, then you can say the kinetic energy, you don't have any heat generated. You have the initial kinetic energies, the final kinetic energy. That gives you a third equation. So it's possible for something like that. He can give you a thing where you have to solve for 3 unknowns. He tends not to do that simply because they get to be really messy. Okay?
So how is that harder if you take away heat? It's fully elastic.
Well, the thing is, he can leave you with another unknown.
Oh, okay.
Yeah, suppose he said, okay, what angle? Now, if it was an elastic collision, he could say, okay, and the tin can goes off with angle theta. So now he's got 1, 2, 3 unknowns. So you say, whoa, I can't do it with just this, but I could do it with energy or kinetic energy. And that is, if it was elastic, there wouldn't be heat. So then I could say that the initial kinetic energy, 1/2 mv squared of this, is equal to the final. That gives me another equation. But now, again, I'm juggling 3 equations, not just 2. So, and plus they have squared terms, which adds to the messiness. They're not like these are linear and they're not so bad.
Yeah.
So he generally doesn't go down that route. Okay, there was, I thought, another hand or something for a question, or maybe that was answered.
The ball drop, that was not a conservation of momentum, you said?
Oh, okay, yeah. What is this momentum conserved?
No, because it comes up that high.
Okay, there's an external force, right? Yeah, you do want to focus on this idea there can't be any external forces for momentum to apply. Okay, let's generalize these ideas a little more, because this is actually some powerful ideas behind this. Let's use this something closely related to momentum is the idea of center of mass. And the idea of center of mass. Let's say you've got some masses here. You could, let's say, what's a big square, a circle, a ball, or something. You might have a little point mass or a little small particle, something like that. You have something that you already know the center of mass in. You can think of that location of that center of mass as the location of the mass. And when you're doing centers of mass, let's say this is, let's say M1, you could imagine all of that piece, as long as you know where its center is, you can replace it in terms of this analysis, in terms of a little point mass of, let's call it M1. I have another one, M2. This thing I could extended body, as long as I know its center of mass, I can indicate its location here as M3, and they sit in space, and could have any number of these things. And I expect the center of mass is going to be, I don't know what these masses are, but it's going to be somewhere likely between them, and call that the center of mass. And we're going to need to be able to locate centers of masses of objects. And when we do this, we need to do some calculations. And we always do this relative to some chosen, and it's really your choice what reference frame you want to use. It's like a coordinate system. You can put it wherever you want. I'll just put a generic one here, sort of an X and a Y this way. I don't even have to angle it like this. And then I can look at the individual positions of these individual pieces. You know, I'm going to have an X1, X2, X3. And I also will have a big X center of mass. I can do this also in the Y direction, and also in the Z direction, and find the Y center of mass and the X center of mass, and also the Z center of mass. And you want to keep in mind that wherever you choose, you need to be careful where you choose, not so much careful, but really clear on where you're putting your origin, because all your measurements are going to be measured relative to that point, and we're going to find the position of the center of mass relative to that point. So let me put that here. So how do we find centers of mass? We can say, well, the X center of mass is going to be equal to, or at least we define it as, the sum of the individual masses, I'll call M sub I times X sub I, all divided by the total mass, M sub I, and this is adding up all the masses that you have, however many. We can do the same thing in the Y direction. We go M sub I times Y sub Y, and sum of all the masses, and could also do that in the Z center of mass, same thing. Z, yeah. And what can be actually handy to do is to deal with summarizing these, and it will be a way of expressing that we can look at the positions of these. The position of this one, I'll call that the position vector, R1. Remember this from basic stuff. This is the position R2. This is the position of R3. And this is the position of the center of mass. And let me use a big capital R for that. That will be R, and I'll put its center of mass. And so we can deal with this. We can say that the R center of mass is equal to, very similar to this, the sum of all these individual pieces, but instead of x, y, and z, we can put them in component form and go R sub I, take that as a vector all over the total mass. So in a sense, this summarizes all three of these steps. Okay, a little note on during your calculations, invariably you do these in both the x, the y, and the z when you do your calculations. And you want to keep in mind that the x center of mass that you end up finding from this equation is going to be relative to this chosen origin. So again, everything's measured from here. These terms inside are measured from this origin, and your final resultant is measured from that origin, both the x, the y, and the z. Okay, now we can, this is just the total mass of the system. We can write this, let me just bring this over here, as m total of the system times the R center of mass is equal to the sum of all the individual pieces. You might say, well, why do we care about this? Okay, what's the point? The physics behind this is good in that if I take the derivative of this with respect to time, taking the derivative of that, take the derivative of this, the total mass doesn't change, but the derivative of the position vector of the center of mass will be the velocity of the center of mass. And when I take the derivative inside here, I go inside here, the masses don't change, but I'll end up with the individual masses times the derivative of the position vector as a function of time. That should be the velocity vector. Maybe I should have, yeah, well, let me do it in one more line here. Sum of m sub I times the velocity of the ith piece. What is this? But this is the sum of the momentum of the ith piece. So that's p sub I. So basically, if we want to get the momentum of the system, it's the sum of the individual momentums. Okay, this would apply to any number of things. So this, I've got three objects here. It could be atoms in a solid. Could be anything. Let me do one more step here. If we take the derivative again with respect to time one more time, taking the derivative here, I end up with the total mass. This is going to be the acceleration of the center of mass. And that's equal to the derivative of all the momentums inside. But the time rate of change, or the derivative of the momentums, is nothing more than the sum of all the forces on the individual pieces. And that would be the sum of all the individual forces would be the net force. Wow, good old F equals ma. Okay, now what this reveals, though, when we play with F equals ma, we are strictly speaking about this acceleration of the center of mass. Now think about this. If we have something like, I've got a hammer here, this idea of the center of mass, I've got a kind of red dot here. It's about where this thing balances, sort of, kind of. Still a little heavy there. Okay, well, that's because it's underneath. I got to do it like this. Anyway, it's about there, okay? Okay, now if I happen to, let's say, I'm not going to, take this thing and I throw it through space, okay, so it's going to act like a projectile. It's going to start spinning, and we're going to see that things naturally want to spin around their center of mass. And what's going to happen is this is going to have a rather complicated path through space. But if you were to focus on this red dot, it is going to be traveling on a parabolic path. That's the projectile part. And it's a great way of taking a rather complex motion and breaking it down. One in terms of its motion of center of mass, and that's what good old F equals ma will give you, the actual acceleration of the center of mass. And then also the fact that this thing is going to rotate around that. There's going to be an angular velocity. We're getting into rotation shortly, but we'll be dealing with that. So very powerful idea. So this is relatively simple and straightforward when you think about it. Realize I left off my vectors here. You don't want to forget that these are all vectors. Okay, now, usually an object, let's say you're dealing with something as complicated as this hammer. There's countless forces and masses inside here. I don't know how many atoms, a lot of them, right? And you think about between the atoms, there can be forces acting. Now, Newton's third law says action, reaction, between every one of these things, these forces between these individual pieces always happen in action-reaction pairs. Those are what we call internal forces. I don't need to, when I go F equals ma with this thing and do some calculations, do I need to worry about the interatomic forces between these things? They're all internal, and they're not, I don't need to concern myself. The only thing I need to do is concern myself is with external forces, something coming in from the outside. So if this is sort of represents 3 atoms in my hammer, it's like this, and what's pulling down is gravity. Now that's an external force. That external force would act on all of these. The reaction pairs are down on the earth pulling up. But if I focus on this as my system, here I have external forces. Momentum isn't conserved there because of the external forces. This thing travels and definitely changes its momentum through space. So ultimately, the sum of the net force is really the sum of the net force is the forces, I should say external forces that are acting. And that's what's key. Okay, now let's step back one step. I'll say, what if the external forces are equal to 0? Yeah, if they're at 0, what can I say about this? The sum of my momentums in my system, excuse me, P, have to be not 0, but a constant. Okay, so if I have this is equal to a constant, and I take the derivative of that with respect to time, I get 0. And if I have 0 external forces, I can go take a step back and say, the sum of all my momentums are constant. This means conservation of momentum. And this would apply, as you can see, very abstractly. These things do not have to physically be connected. You kind of think of all these atoms in the hammer being connected, but there's actually spaces between them. This could be the stars in a galaxy, forces between them, and dealing with external forces, maybe from an outside external galaxy affecting their motion. Can be very powerful and very simple ideas. And the big catch for all of this stuff with conservation of momentum, if you have a system and there is no external forces, then you can be assured that conservation of momentum applies. Okay, so again, okay. Now we're going to be doing some calculations of center of mass. We need, and typically he'll, rather than as a separate problem, he'll tie it into some other problems. And I'm going to be doing some, but we want to build some other ideas first. And then we're going to revisit center of mass several times here. Okay, any questions? Okay, what else did I have on my list here? Okay. Throwing the hammer, oh yes. Okay, for real this time, right? Okay. See if I can catch it. Okay. Sorry if my voice is a little off. I'm down with a cold this week, but luckily I'm feeling a little better. Okay. Okay. Let me clean the board here a bit, and where's my rags? And let's get into some rotation. When we get doing some rotation problems, we'll definitely need to be able to calculate some centers of mass. So, okay. Okay, let's start generic. Okay, let's say we're just going to travel in a circle. Let's just talk about circular motion for a minute. Let's say you're going to travel around a circle of radius, let's say capital R, and you're going to travel around an arc. Let's call that arc S. And we want to relate, you could say it's speed that you're going around here, or we'd say the tangential velocity would be ds dt is how you think about it as you go around, just distance being measured the arc around this thing. Now what will be handy for us is to talk about angular velocity. It's going to be a potent idea. And what I would suggest is imagine putting a unit circle superimposed on top of this. A unit circle of radius 1, and its arc that it kind of represents the same, kind of the shadow of your motion on the unit circle. This arc is going to be theta. It will be in radians, not degrees. So I'm going to use a little subscript to remind us of that. And there's some simple relationships we can get by using the circular motion. We can say that this kind of piece of the pie here with s and this arc on the unit circle, which is analogous to the arc on the larger circle, we can do simple proportions. I can say, well, this arc s is to r as theta in radians is to the unit circle radius 1. Or s is equal to r times theta. And again, know that theta has to be in radians. So we'll use this relationship a great deal. If we want to get at velocity, I see tangential velocity is ds dt. I can say the tangential velocity, ds dt, taking the derivative here. Take the derivative, now as long as I stay at the same radius, I only change my theta, d theta dt, and we give a special symbol for that. For what is that? That's omega, and that's what we refer to as the angular velocity. Okay, and we can do one more thing. We could take another derivative, and we can say the tangential acceleration is the derivative of the tangential velocity. If I want to speed up or slow down, take the derivative. This is going to be r times d omega dt. And what's d omega dt? Yeah, we call that alpha. So these are the standard ones we're using throughout, and so you should be comfortable just looking at these terms and realizing this is now the angular acceleration. I can't write fast enough. Okay. So these are key relationships. I think it's good to just kind of see this. I've seen a lot of students, they kind of lose sight of the basics behind this, and you kind of get looking at these expressions and you just kind of all these symbols and things banging around in your head. It helps, I think, to go back to the basics, to help sort them out, to see what's going on. Now, what we'll do for things, let's start with a rigid body. We do a lot with rigid body rotation, and it could be any kind of body. I'll just draw my typical, cut it out of a sheet of steel or something. And I can, let's say, weld a little pin on it. It's an axle, and I can get this thing to rotate with some angular velocity. And the idea of angular velocity is good for a solid piece because individual pieces inside here, let's say a little piece here, m sub I, is got at some distance r sub I from the center, and it's going to have some velocity v sub I here. There's going to be another piece that's maybe over here, closer radius, r sub j, and that's m sub j, and it's got its velocity v sub j. And I could do this for this whole thing. We do realize that the velocity, even though the velocity of those individual pieces are different, in fact, glad to had me get this out. This idea of these styrofoam balls, they're all traveling different velocities, but as they rotate with the wheel, they have the same angular velocity. We now can make use of this idea that their individual velocities are related to their angular velocities. So I can say that that is going to be r sub I times omega. I lose myself here. That's okay. Now, if we want to do something, let's say I've got an object rotating with some angular velocity, we could say it's got some kinetic energy. So if we want to look at what kinetic energy it's got, anytime we have kinetic energy of a system of things, we just sum them all up. And we'd sum them up, m sub I, it would be 1/2 m sub I times v sub I squared. Okay, so that's all of the kinetic energy that we're used to. Now, we can do a little bit of math here, though, since we're summing them up. Well, one, I could factor out this 1/2. I wouldn't need that. And I have the sum of m sub I, and now v sub I could rewrite as r sub I times omega. I'm going to square that. And I could square both of these terms inside. And I could, since omega is the same for all of them, I could factor that out. So I'd have a 1/2 omega, and then I'm left with the sum of m sub I, and I'm going to have an r sub I squared here. And what's that?
Omega squared?
Yes, thank you. And omega squared's there. Yeah, they squared them both. Yeah, thanks. I'd be scrambling here in a moment. Okay, what is this? Yeah, okay, this pattern is going to show up. It turns out that all the kind of geometry that's left behind is locked up here. I can't factor these things out. They could all have different masses. Maybe the densities change. It could be something complicated. They're all radii changes, so I can't pull them out. But I can group them all together, and we call this the moment of inertia and give it the symbol I. And the kinetic energy is just 1/2 I omega squared. Okay, so now you want to keep in mind that this really came from 1/2 mv squared. So there's nothing fundamentally new. It's a little recasting. It's very handy for rigid bodies that are in rotation. That's a good way to get the kinetic energy. If you have something like a bullet and something rotating and you want to get the kinetic energy, it's okay to, we're just summing them all up. So some things it might be handier just to use 1/2 mv squared. Other things like rigid bodies that are rotating, it's usually handier to do this. But you just add them all up. And in terms of keeping things straight, remember ordinary kinetic energy is 1/2 mv squared. And the velocity is somewhat analogous to angular velocity, so this can kind of help you remember it because we've got a lot of things to remember for the exam, and he doesn't let you have any notes. This I is somewhat analogous to mass. And a lot of students say, well, you know, I'm trying to get my head around this. What is moment of inertia? Inertia in general is, well, think about mass. How many know what mass is? Do you know? Well, I don't either. Nobody knows. We don't know what mass is. We get used to it, and so we start to, and we can do problems with it. We say in general, Isaac Newton didn't define it either, did he? He said F equals ma, and he didn't define. They was using that to define force, but he never defined mass. But mass was just this inertial property. What inertia was something, if a mass that's light is easy to get to move. Once it's moving, it's easy to stop. If it's got a heavy mass, it's difficult to get it to move, or once it's moving, it's difficult to stop it. From that same analogy, you can think of rotational inertia, something with a lot of rotational inertia. If it's got a lot of it, it's difficult to once get it to go. Once it's going, it's difficult to stop. And so that is this basic idea of inertia, which we really don't know too much more than that. Of course, we're defining it this way. Ordinary mass, it really doesn't matter, you know, if you're going to weigh something, you know, whether you weigh it like this or like this. Any way you weigh it, the mass is the same. But as far as rotational inertia, it definitely matters which way this thing is going to rotate. You get different answers depending on how you're going to rotate that rigid body. So there are these subtle differences. Okay, so that's basic kinetic energy. Let me do a little quickie example for that. How about if I'm going to take an object, let's say a disk, and let's say we hang a mass on it, and we let this mass drop some distance. So let's just call this big M and this little m, and it's going to fall some distance, distance y. Is it falls. And what are we looking for? We're looking for maybe what its, let's say, what is its velocity as it falls here? It starts, let's say, from rest. It's going to fall and come up with some final velocity here. That means that this thing is also going to be rotating with some final angular velocity as this thing, that is, when it passes here. We can use energy to find this. Just as we did before, we can set our zero wherever we want as far as potential energy. We're going to say the initial energy is equal to the final energy. The initial energy, well, let's see, what do we want to do? Let's, how about if we make this, this here, bottom of the block, zero potential energy. Potential energy equal to 0. It's going to fall, this whole distance y. And so it's going to end up at 0 potential. So I could say the initial energy is going to be kinetic energy plus potential energy initial. And then the final kinetic energy or final energy will be something else. Initially, these both start at rest. There's no kinetic energy. The potential energy is just this small mg, and its h is y. And that's going to equal the final energy. Now we've got both of these things that are going to be rotating. And the idea is that this thing is going to be coming down with some velocity. This is going to be rotating. This thing should be rotating with some angular velocity. And the idea that there'll be a tangential velocity that should, if this string wraps around this thing, should be the same as this velocity. And hope you see that. Let me plow ahead anyway, and we can go back and pick up on some of these ideas. There's some subtle things going on. The final energy is going to be the final kinetic energy. It's going to be of two parts. It's going to be the K final of one of the roller or the disk, and plus the kinetic final of the mass. Plus any potential energy that we've got, but I've got it arranged so that when I get down to here, the potential energy is 0. Okay. Ultimately, we only care about changes in potential energy. You'll notice I didn't include the disk. I've got this thing pinned here. It's not going to change height, and so it's not going to change its potential energy. This is the only thing we need to focus on as far as a change in potential. So, subtle issues. The kinetic energy of the disk, here's where we can use this 1/2 I omega squared plus the K of the mass. That's just 1/2 mv squared is fine. And that should be just equal to mgy. We've got this relationship here that as this thing rotates, the tangential velocity is going to be equal to the radius of this thing, r, times omega final. And that's what we'd be dealing with here. Or for our purposes, let's go omega final is v tangential all over r. And so that's going to be 1/2 I. Oh, and I'll come back and get I in a moment here. But this is going to be v tangential all over r. And we're going to square that plus 1/2 mv squared. We need to know the I of the disk. I'm going to give it to you. He will give you moments of inertia around the centers of mass. You maybe already know this. For a disk, it's going to be 1/2 the mass of the disk. I'm calling that capital M. And then that's going to be r squared. So we've got that. And so now we're ready to do this. One note here, that as long as this string doesn't slip on this thing, I expect that the velocity of the string should be equal to the tangential velocity of a point on the rim as this thing rotates. Hopefully that's obvious. So that these two v's are the same thing. This r squared is going to cancel this. This pattern often shows up, and so we're going to have mgy is equal to now 1/4 mv squared plus a 1/2 mv squared. We can do a little factoring and get a v squared. I've got a 1/4 and 1/2, 3/4. Bring it over to the other side. So that's mgy minus 3/4. No, this is a small m and a big M. Can't do that. I can do this. Minus 1/4 big M plus 1/2 little m. And that would be v squared. And we could certainly take the square root of that to get v. Maybe come back to this idea. Clearly, I didn't give you any numbers here, but we could certainly plug those in and come up with what that is. Okay, so this is just kind of an example of how we could maybe apply this kinetic energy in both translational for this piece here and the familiar 1/2 mv squared, and also the rotational.
I is equal to mr squared, right?
I should be mr squared. Okay, now that's for an individual little mass. Now this is for a whole disk. Okay, and in fact we're going to do a little calculation for moments of inertia here in a moment. We're not going to do too much with it because he has gotten away from doing too much of that. Yeah.
I think it was last week you did one that involved heat with the center of the pulley. Is this a frictionless pulley or something?
I'm making this a frictionless pulley. Yeah. If there was some friction in there, that could be an added complication in which you could have losses. And you've got some with, you do have a homework problem or two with that, like torque due to friction.
So you said he's going to give us I?
He will give you I. He will give it about typically the center of mass. Now you may have to, and he's good about that, and he doesn't, even a disk, he'll give you the disk. Yeah, right. So he will do that. However, you may need to use the parallel axis theorem, which I'm going to get to maybe change the axes. He'll probably expect that to happen. Okay, let's see. I have four. Okay. As far as this idea of calculating centers of mass, the idea that I is equal to the sum of m sub I times x sub I, r sub I, squared. Okay, summing those up. If we have an extended body we may have to do that summation in the form of an integration. And if we have to do that, we're going to break the thing up into a bunch of little pieces. You're going to think of if I was having this piece, let's say I was rotating this, and I wanted to get its moment of inertia. I'd have to break this thing up. You could imagine this is a great calculus problem, double integrals here, breaking this up into a bunch of pieces, and there'd be a little tiny little piece here. Now this piece is going to become arbitrarily small as you make it smaller and smaller. This is going to be what I'll call a little dm, a differential mass. It'll be very small. The radius, the distance from the axis, could be fairly large. So in terms of doing this as an integral, we'll do it this way. We'll say that summation is replaced with an integral sign. The r, again, is not necessarily small. That's going to be an r squared, but we will have a small dm, a differential mass, that these are the little pieces that we're going to need to sum or integrate over the body of the thing. So that's its kind of integral form. Okay, let's do something that involves this. I've got one here, and he has done this one. So I mean, it's not. These are all his questions. When he first started teaching here, he used to always give a moment of inertia problem that was fairly meaty, and that you had to know how to do things like a disk, a hole with a disk, and he would give variable densities, and get the rotational inertia of a pyramid around a point, and just crazy stuff. But he's kind of backed off. He says, okay, that's more math stuff, and we got better things to do. But let's do one thing here anyway. In fact, you probably have done moment of inertia problems in math, and when you're doing them in math, you don't know what you're doing, but you're just doing it. Let's say we're going to rotate a rod of length L around its center of mass. Okay, its center of mass would be dead center, obviously. This is number 4 on the practice problem, so this is where it is. And we're supposed to show that it's this familiar 1/12 ml squared. So, okay, now it's got some mass to this thing. And we need to break it up into a bunch of pieces. Now it is going to be we're assuming it's a thin rod, so that's arbitrarily small. I'm going to suggest that, well, maybe it's got a little bit of cross-sectional area. Maybe it's circular, maybe it's a square cross-section. I'm not terribly worried about that. I'm going to put this thing on the x-axis, and I need to break it up into a bunch of slices. And that's kind of my typical slice. Always draw your kind of typical one. Don't draw the one at the very start or the very end. I am going to break this thing up into a whole bunch of pieces. This particular piece is going to have some x will be its position. That's effectively its r. And it's going to have a little bit of thickness. Little dx is going to be its width. And it's going to have a little bit of volume to it. That's going to be a little dV, and that dV, that volume of that thing, should be the cross-sectional area times dx. And then ultimately, we also want to get at that this little piece has a little differential mass, a little dm. Okay, and we need to find out what that is. Okay, and that part gives people a little bit of trouble. Okay, what I would suggest is there's lots of ways we can do this, and some that are relatively short, like with linear density, but I noticed that a lot of people have trouble with these basic ideas. Most people are a little more comfortable with ordinary density as we know it. Density, we say, is equal to mass over volume, right? From that, we did that in the first week. And the mass of this thing is m. The volume of this rod would be its cross-sectional area A times L, and that would be its density. And once I have this idea, I could go with the volume and then come back down here and get the differential mass. So let me put that in kind of several steps here. The differential mass should be, the mass of this thing should be the density of this times its small little differential volume. Its differential volume is going to be its area times dx. And if we put this idea of the density in with this thing, the density is the mass over the area times the length. Okay, so that's density times the area times dx. And you'll notice that the area drops out. And we didn't really need it. It ended up being just the mass over the length times dx. And it's quite possible when he was doing this, he maybe just went right to this step. And very often this is something, the mass per unit length is something we'll use the symbol lambda for. It just represents how much mass do you have, how many kilograms of mass per meter of stuff that you have. And it works very well if this thing is very uniform. We can just say, well, how much per meter? Rather than going all the way back to ordinary density. But if you want to take it there, you can. It just ends up dropping out. Anyway, we do have what the differential mass is. It's just going to be m over L dx. If you don't like that one, you can also do it as a kind of proportion argument. You can say, well, the mass of the whole stick is to the length of the stick as the mass of this little piece, dm, is to its length. Well, its length is just a little dx, a little tiny one. And then you can come back to right away to here again. So lots of ways of thinking of how to get that mass, but we need to do that to do the integral. Yeah?
What's that little, define the little A symbol again?
The A symbol represented the area.
No, not that.
No.
The weird curly A.
Oh, this thing?
On the top, it's the lambda.
Oh, this is lambda. This is the Greek letter lambda. Lambda, okay. You'll see it again, so you might as well get used to it. It is this funny looking, I'm not drawing a real good one here. It's a good example, but it's the Greek letter lambda. It often gets used for what we call linear mass density. get into 122, we'll be using for linear charge density. So I mean, it's kind of part of the lingo. What does it represent?
What does it mean?
Okay, it's merely a symbol. It represents how much mass per unit length, like this meter stick. If I weighed this thing, what's its mass for a meter? And if I said, well, if you had 5 meters of this, what should you have? Well, 5 times that. You know? Or if you had half a meter, it's half of that. So it's just a way of breaking it down. But people do get spooked by all these terms, trying to keep everything straight in their heads. Okay, let's go back to the calculation. I would calculate this thing. Now, the moment of inertia, I need to add up the inertias of all the little pieces. And as I do that, I'm going to sum. This is going to be r. In this case, the radius of this thing is going to be an x squared. The dm, let me just put it as dm right now. And I'm going to, let me go one more step here. X squared. My dm was m over L dx. Okay, and I'm going to break this thing down. I need to really integrate the whole thing. I need to go from the minus L over 2. Okay, the whole thing is L. This is L over 2. This is L over 2. I can go, if I want, I could go 2 times and just integrate from 0 out to L over 2 to go out to the end of this thing. And then because I'm doubling it, I'm just adding this up and along with that. So hopefully that's reasonable from your calculus experience. And I end up with 2m over L, factoring that out. And I'm left with an x squared dx from 0 to L over 2. Let me do it quick and hopefully not make any mistakes. You'll be watching. This is going to be x over 3. And this is evaluated from 0 to L over 2. I come up with 2ml, and I've got a 3 here. And then this is going to be x cubed. This is going to be L over 2. We're going to cube that. And that should be, when we cube 2, it's an 8. 2 cancels with that 8 to make a 4. 4 times 3 is 12. And I come up with 1/12 ml squared. Okay, and that's what he wanted us to show. Okay, so that's kind of a little example. We could do more of them, but I think that will be the only one we'll do today.
Do you think you'll have us do that, but calculate, say, like a ring? Is there a chance that we can do that on the exam?
I think he just has his memories.
For the most, I haven't seen him do it in some time. Now, a ring itself is just going to be mr squared, right?
Yeah, sure.
So, I mean, that's fairly trivial. That would be a trivial one. A disk, a little more advanced, but not too bad. Yeah, Gabe?
Just back to the old problem. Is that right?
This?
You take out the v, then wouldn't you divide? Would it be mgy divided by 1/4 m?
Yes, you would. Thank you. Yes, I screwed up. Okay, I'm trying.
That was his idea.
No, okay, thank you for catching me, because actually I want to come back to this problem, and I did mess up. I factored out the v squared. I have to divide through by this. I thought that looked a little weird, and then okay, you got to watch me. I do these things. My dyslexia here is 1/2 m. Okay, so I think I got it right this time, and then with the square root we can do that. Okay, yeah, thanks. Okay, and I wanted to leave that up there. Parallel. Okay, as far as calculating moments of inertia, that's let's leave that. Something that he really loves is he'll give you the moments of inertia. Sometimes they're right on the front of the test. You know, the moment of inertia of a rod, the moment of inertia of a disk. We'll lay those out for you. But they'll all be about the center of mass. Now, one thing that he loves is this idea of the parallel axis theorem. And here's how it works. I'm not going to derive it here. We haven't got enough time for all of this. It's done in the book, and if you check your notes, I'm sure Dr. Young did it. Let's say you have an object. Well, let me give a more familiar object. Let's say we've got something like something like a disk. And its center of mass, of course, is dead center in this thing. And we know that the moment of inertia, or it maybe gives it to you, the I of the disk center of mass is going to be 1/2 mr squared. And let's say we want to rotate it, but not around its center. We want to rotate it about some other point in space. It doesn't have to be on the object. Let's say it just can be some point in space. Since this is the center of mass, there's going to be some distance between this thing and the center of mass of that, and we want to get the new rotational inertia. It's going to change. If I try to rotate it around a different point in space, this disk is going to be going around like this. And I can get the moment of inertia about this other point. If I know the moment of inertia about the center of mass, then all I need to do is add the mass of this thing times this distance from the center of mass to this new point of rotation squared. And that will give that to you. And this is something we're going to be using as we do some more problems here. Just for fun of it, let's try this idea of a rod. This was a rod about its center was 1/12 ml squared. So let's say we want to do the moment of inertia. Let's try to do this. Let me draw a new picture here. This would be the rod. We know its center of mass is, of course, in the center. Let's say I want to rotate it around the end of this thing. That would be I about this point. And we want to get what that is. So again, we're rotating around the end of the thing rather than around the center. Well, we can use the parallel axis theorem for that. As long as you know the I about the center, and it has to be the I about the center, and I know that this is 1/12 ml squared, plus the mass of this thing, whole stick, times d. And d would represent the distance from the center to the new point of rotation. And in this case, that would be L/2. And I square that. So when I do that, I end up with 1/12 ml squared plus now a 1/4 ml squared. You can do the math as well as I, better. It's going to turn out to be a 1/3 ml squared is going to be the moment of inertia around the end. So I was able to get that. Okay, and the table in your book gives a number of them. It gives the I about the end point as well as around the center. But maybe it'd give you the I about the center and have you show that it's going to be 1/3 ml squared. Or, as you'll see, he does this parallel axis theorem a number of different ways. Let's try a little problem that, let me pose it this way. We've done the meter stick, moment of inertia calculating around the center. We want to do it also about the end. How about if I made the problem here and said, suppose we're going to hold this meter stick here horizontally, and then I'm going to drop it. And the idea that as it falls, he wants to get the speed of the tip of this thing just at the bottom as it crosses the bottom. Okay, this is a problem that he's been asking a whole bunch of different ways over the last number of semesters. So this is a good one to pay attention to. Okay, let's try that. We can use conservation of energy is the best way to do this. There's going to be a problem if you want to say, oh, I want to do torques. There's going to be mg. The problem is as it comes down that the torque is changing on the way down. It's not constant. So if you try to do it, you are really getting yourself in deep as far as being able to not do it very well. Let's do this with energy. And Okay, so I'll draw the picture here. Let's see, we got a meter stick out like this, and it's going to swing, and going to swing down. Let me just call it L for now so we can see kind of conceptually what's happening, because how long is a meter stick? He likes this one. Okay, we're going to start from here. Now, the center of mass of this thing is up to here. And there is a couple subtleties in here. As we drop it, of course, the kinetic energy initially is 0. So if I do energy initial is equal to kinetic plus potential. Oh, let's see. Where should we put 0 potential energy? At the bottom? Okay, let's do that. Let's say gravitational potential energy is going to be 0 here. Okay, the initial energy, well, it was started from rest, that's 0. The potential energy up to this thing should be mg, and h is, well, let's just say L for now. No, it's going to be 1 meter.
I have a question.
Yeah.
Does it matter for the L or the height? Should we use the center of mass as the height or the bottom of the
You raise an excellent question. Okay, let's tease him first here. Okay, this energy final is going to be kinetic plus potential, or gravitational, potentially potential. I'm going to have a kinetic energy is going to be 1/2 the I about the center of mass times omega squared. Okay, and this is going to be I about the end point, P. Okay, so that's going to be this 1/3 ml squared. Well, yeah, what about the issue of potential energy? Is it 0? Okay, now this is a bit tricky when you think about it. This end piece, did it change in height? Whoa, okay. Now this piece over here swung down to here. Wow, okay, so it didn't drop the whole distance. So at the end, doesn't it still have some potential energy? And even this piece swaying down, it's sitting right about here. So they're all at different heights. Ooh, what to do? Okay, I could prove this, but let me just tell you what it is. And then we can debate about it. If maybe you can figure this out for yourself once you get thinking about it. The idea that the center of mass is here. Okay, so a big point. Center of mass is located at this position. The center of mass changed from here to here. This is the nice thing about center of mass. It can tell you a lot about the system. We will say that the idea of the potential energy is going to be mg, and it's going to now be at L/2 will be its height. Okay? Now, if you want, I can give you kind of an imaginary argument here. To show you this, we can take, with the idea of energy, it doesn't matter what path we take through space, whether we swing or whether we pick this thing up. If I pick this thing up and I say, oh, okay, its potential energy is right here, that's at the center, and I could lower it to here. Okay, so I've dropped its potential energy L/2, height of L/2. And then if I brought this end down, but also at the same time raise that end, is there any change in potential energy there? So if I raise it up to there, and then slip it on the rod, okay, did you see my argument a little bit? Okay, so I really just took it down, I lowered it halfway, and I cranked it into position. And I've got the position of the center of mass will tell me about the whole system. If you want to literally integrate this, actually the integration isn't bad. The MGHs are very much like the idea of finding the center of mass, and that's what you're going to end up doing. If you do want to do this for everything and integrate along this thing, you will find yourself at the center of mass. So this is an important idea that you have that, and this is key to doing a number of problems that are like this. So then you can go ahead and set these two things equal. The initial energy is equal to the final energy. MGL is equal to 1/2 I p omega squared plus mg L over 2. And I bring this back over here and subtract that. So that's going to be a 1/2 mgl is equal to 1/2 I about p times omega squared. Maybe I shouldn't even do any more here. You could go on. We could go ahead and get, an I about point P. We do want to use a 1/3 ml squared for that. We could go ahead and get omega, but that wasn't what he asked for. I guess you don't have the problem in front of you. In this, what I asked for the speed of the thing at the very bottom. You would get omega final right at the bottom, and then you could say that if you have omega final, you can get velocity final. That would be the omega final times the length of the rod to get at what just the tangential speed at the bottom is. Okay, he's asked this a number of different ways. In fact, he's got one here for you on these extra problems. Take a look at number 2. Okay, a little different twist. He's been asking this different themed. This is a little more complicated. He doesn't have it starting out horizontally. He has it starting up here. And he's got these discs connected. And it's going to rotate around this point, and then it's going to swing down. Okay? This issue about the center of mass. Where's the center of mass of this arrangement here? I'd say it's in the center of mass. Okay? And it's going to swing down, and it's going to swing down here. I've got the solutions here that I've worked through that you've got access to. So maybe try this on your own. But now in this problem, though, it's also interesting that he asks you, you need to calculate the moment of inertia of this thing. Okay, he'll give you the discs and the rods. You can do that.
Add them all together.
Add them all together. Okay, these discs use the parallel axis theorem. There's going to be a D for those that is going to be off in this direction, so you want to watch that. The individual masses, the rods. This rod also is rotating. You want to use the parallel axis theorem for this rod about this point. It has a distance D of half the length of the rod. Okay, I've got the details in my notes. We've got a lot of ground to cover, so I'm not going to do that. But anyway, between you and your study partners, hopefully you have study partners that you can kind of resolve any of those issues. Again, he's done this a number of different ways, but it's the same basic problem. It's a real simple one with energy, or as simple as long as you have these key ideas in mind. Okay, something that is important as far as energy. Oh, again, I want to hang on to this one for just a bit here, I think. Maybe I don't. No, I'm going to let go.
So Don,
Yeah.
on that problem, a big concept to understand is when you're using energy,
Mm-hmm.
you need to measure the change of potential energy from the center of mass.
Right, and that's the big lesson. Any kind of potential energy problem, this idea of center of mass is really key. You say if you're going to lift something, what you're lifting is this. Where is the center of mass? So if you're changing this thing somehow, how does the center change? It goes from one point up to that point. It doesn't matter on anything else that goes on. So it can help you, keep things straight as far as what's going on. The key idea. Yeah.
That's when you're using parallel axis basically 3 times, right? For all of both.
Yeah, the 2 discs you can kind of got to. Yeah, you've really got 3 that you. One is the rod, which you maybe already know is the 1/3 ml squared.
Right.
This is a 1/12 ml squared plus L over ml over 2 squared,
Right.
which will end up being actually 1/3, the same as this.
Okay.
You maybe find that. And then the disc, once you do 1 disc, you can say times 2. That'd be fine. Okay? Okay, now this parallel axis theorem is a handy one for doing other types of problems, or having a basic idea. We've been talking about like something that's rolling, or actually right now we've dealt with things that are spinning on their axis, but something that we use a lot are things like that are rolling. Now if something is rolling, and the key word you'll want to see in problems is rolling without slipping. Okay, that means the surfaces aren't skidding. It's not doing this kind of thing, but it's pure rolling. Yeah, another use of the word. And as I rotate this thing, of course, it advances forward. And if you look at the arc that this thing traverses and the distance that it moves, they're going to be the same. And so the idea that the speed of this thing, without going into too much detail, I hope it's reasonable, that the velocity of this thing, its motion, we say it's translational velocity, that is how it's moving horizontally, compared to its rotational velocity or tangential velocity. As this thing is rotating, it rotates through this angle, this rotational velocity, which is just the velocity around this distance, is the same as the velocity that this thing moves forward. So when you're rolling without slipping, we would say the tangential velocity is equal to the velocity of this thing rolling. Hopefully it's one of those kind of clumsy ones, and until you see it, feels a little weird. But the idea that if you are rolling, actually rolling motion, strictly speaking, on an instantaneous level, is that you are really rotating around a single point. That point on the ground that you're making contact with, you are, in a sense, rotating around that point. You're not truly rotating around the center. With that little bit of rotation, you are really rotating around the end point. So let me say this, that the idea that you are rotating around this point, let's look at the energy here. Well, the energy is going to be 1/2 the I of this wheel or disc, I'll just call I, times, and it's I about point P, that's this point on the rim, times omega squared, and that's the actual, we should call it kinetic energy, okay? And with the parallel axis theorem, we can say that I about point P is the same as I about the center of mass, plus the center of mass, of course, is here, and the distance between the center of mass and that point is the radius, and so that's going to be equal to the mass times r squared with the radius times omega squared. We can break this into two parts, 1/2 I about the center of mass times omega squared, plus 1/2 m r squared times omega squared. And we know that if it's rolling without slipping, the velocity should be equal to r times omega, or what I want to do is omega is v over r. And if I put that in here, 1/2 I. Well, let me do it for, I want to leave this as omega. I could make the substitution there, but I want to make a point, 1/2 m r squared, and then this is going to be v squared over r, v over r squared. These r squareds are going to knock off, and I'm going to have a 1/2 mv squared. So this is a 1/2 I, and this I is about the center of mass, let me emphasize that, times omega squared, plus 1/2 mv squared. And that v is the velocity of the motion of this thing. The velocity of this thing along the direction of motion is the velocity of that center of mass. And that's the kinetic energy. Now this is something we call rolling energy. And you want to keep these two terms straight. Now, actually, we are coming back to the idea it really is instantaneously rotating about this point. All of these masses have their kinetic energy. It's, in a sense, all tied up in this. With the parallel axis theorem, it allows us to break it into two parts. Now, sometimes you can sort of think of them like components. That's really misspeaking. It's really kind of a mathematical trick that we've done with the parallel axis theorem, but it's really handy. We call this motion, 1/2 mv squared, we call this the translational kinetic energy, and we call this term the rotational kinetic energy. And really, you can look at rolling motion as the sum of the two of them. And that's probably, once you get used to it, it's a very convenient and kind of an intuitive way of thinking. So if something is rolling along, it is doing one of two things. It is translating, and it's also rotating. And you want to consider both those forms of energy. And just add them together. Okay. So again, these are going to be some things we're going to be using. Okay. Okay, let's see. Let's do one more topic here, and then we'll take a break. Or do people want a break now? Ready for a break now? Yes? Okay, yeah, let's take about a 10-15 minute break, and then we'll come back and do a little more with rotation and finish up. Luckily, you don't have to